So this is sort of historically been my least favorite uh, part of thermo. Well, my least favorite thermodynamic function, the enthalpy. Who came up with that name? Oh, by the way, so today's Friday the 13th, and we have one important thing on our schedule between today and our next holiday, which is Halloween, right? And what is that? There's a midterm, right? Yeah, October 30th. Just to make sure that you're all aware of that. Any questions so far? So I have a couple questions. If you don't, so can you view the lectures online? Yes, and you're caught up with all the documents that I owe you, right? Good. Pardon me? I do record my lecture. I mean, I gave permission. If I recorded it, I'd forget to do it, but it's automatically done, and it should be available on the course website. UJA, right? You know what I'm talking about? UJA? I'd never heard of that before. Yeah, yeah. You can find them if you want to watch them again. Yeah. Question? Yes. Question about the midterm? How many questions? I don't know. I will give you not very many, okay? But like question one may have 12 parts. You know, there's that kind of thing, okay? But I will give you a sample midterm that will look a lot, you know, it'll be the same font. What I'll probably do is I use LaTeX. Anybody here use LaTeX to write documents? Congratulations, extra credit. I will take the LaTeX file for the sample midterm and I will modify it to make the actual midterm. So the font will be the same, et cetera, et cetera. And the length, you know, you'll get an idea for the length, okay? And and just as in the last homework assignment, there may or may not, depending upon, you know, how much coffee I've had, be a harder problem at the end. So the last problem might be like the problem that is on the last one on your homework solution. That's actually quite a hard problem, and I will work that problem, at least sketch how to do it at some point. But it's worth thinking about like how I would do it, or it's worth if you think about how you would do it. Of course, it's also good advice for myself. Even if it's too much like algebra to do, having the strategy is important. Okay, so that's like a real problem. You know, it's not straightforward. It's not just following a simple process that you've committed to memory. You have to kind of think about it, and of course that's what it's all about, isn't it? When you get out of here. Should you be able to get out of here, right? And then the life does not, it provides problems that are a little bit more challenging. Let's just put it that way. Okay, so you've been having discussion sections today. Okay, good. Yeah, let me know how those go. If there's issues, just shoot me an email. Yes. Yeah. Yes. In principle, I do, but I have to figure out, I have a list of concepts, which I will also give you, at some point, I basically have a list of, topics. Now, I have to update that, because the last time I taught this class, it was even though it was Atkins, somehow it's changed. This is the first quarter, it used to be the third quarter. Why do people do this? They just keep stirring the pot to make things difficult, keep it interesting. So I will give you an updated list of concepts like first law, second law, and yes, there's like the list of concepts for thermo, which you could probably figure out for yourself. Ask ChatGPT. Probably it would lie to you, but they would give you a list, right? But you're interested in what's going to be on the midterm, right? So I'll make it clear, like how far we'll go. Most likely there will be, and one reason why I kind of wanted to have a little bit later is because there'll be like a line we'll draw that will be not the day before the midterm, right? But maybe, two lectures or so where we'll draw the line so that the stuff that just happened in lecture is not on the midterm, and it's more the past, as it were, okay? So I'll make that clear. Anything else? I mostly no, because so I gave you homework set, right? And there was one where you brought the two blocks together. That was pretty straightforward, I thought, but maybe, it's not a hard problem, but it might be, because you get an abstract answer. Maybe that might even be a little bit, if I gave you that on a midterm, I'm not sure what the yield would be. But then the next problem, okay, the isothermal compression of a gas, that's like a midterm problem. So I end up always doing this. So here's something that happens, okay? I do an adiabatic expansion or something like that. So the adiabatic compression is actually, why is that problem hard? We will talk about it, but if I compress a gas reversibly adiabatically, what happens? Okay, isothermal one I can do because the temperature, I always know what the temperature is going to be. I compress it slowly, I compress it with a constant force, so I do it more rapidly, I do more work, but because it's isothermal, I always know what the final temperature is. Because if I do more work, just more heat comes out. But with the adiabatic one, all the work I do stays in the gas, and it changes the internal energy of the gas. So if I do it reversibly, the energy of the gas goes up, the temperature goes up, right? Right? That's intuitively, right? I do work, and the energy can't go anywhere. It's got to be in there. If I do it irreversibly with a constant force, I do more work, right? So the temperature is different for the two cases, and if I do it reversibly, you just have to. It's like a standard problem. But if I do it irreversibly, and if I'm aiming for a given final volume, right? So the way you do that, if you think about how we did it for the isothermal one, you need to figure out for isothermal gas compressing with a constant force, you need to figure out what that constant force is going to be, the external pressure, so that the internal pressure is equal to it when you're at half the volume, right? Because the gas is going to keep compressing until its pressure's gone up to the point where everything is in balance, right? Right? Now, when you do it with the adiabatic one, now the temperature depends on how you do it. And so it's going to be hotter, when you do it faster. And so and if it's going to be hotter, the pressure is going to be different. So you're going to have to use a more pressure, like the faster you do it, the more pressure you're going to have to apply to get to the same final volume if that's your target. So you have a little bit of math to do, right? But that's what I mean. Like I hope you can kind of figure out. And this is all really, it's common sense. As long as you have this picture in your mind that if I'm going to compress this gas, its temperature is going to go up, and the more work I do doing that, the higher its temperature is going to go. That's the kind of stuff that you sort of know just from life, but you forget when they put a chemistry label on it. Okay, because then you fall into whatever way of thinking you use when you go to school, instead of trying to figure out how you're going to pay for your education and things like that. You're all good at that, but not necessarily when there's math involved. Okay, so but on the exam, to get back to that, there's some problem that you'll do, which will be more straightforward. But then I'll ask you everything about the problem. So it'd be like a full audit from the IRS. So all the stuff you're not guilty of, they'll look at that. But then there's the interesting part, that they'll get to. So like for instance, you do an isothermal compression of a gas. The initial temperature is T naught, and then you calculate how much work, what's the heat, what's the change in internal energy, what's the change in entropy, what's the final enthalpy. If I ever get to it, we'll talk about enthalpy. There's all the different things you could ask. And I'll say, what's the final temperature? Right? That's part of everything. Now, is that a hard problem? Is it? So you'll fill the back. Because if the initial temperature is T naught and I do an isothermal compression, what is the final temperature? T naught. Okay. This is what I mean. Now, is that hard? Is that tricky? You just got to think. What it encourages, I suppose. Who knows what it really encourages? Like, not coming to lecture, but it encourages having a complete sort of understanding of the problem. That's what you have to do in thermodynamics. It's hard because you can do that. You can understand it. And it's not just like coming in and using one formula to take these numbers and get that number. That's not, you can do it that way, but the way I do it is you're going to do this process we've talked about, and now you should understand everything about it, including the obvious and trivial things, like if the temperature doesn't change, then the final temperature is the same as the initial temperature, and it doesn't require you any work. You might just say, like, isothermal, obviously, okay, you might write, obviously it's this, exclamation point. Stop asking stupid questions. But it's not a stupid question because some people will get it wrong. They'll insist on doing a bunch of integrals on the back of the page because they can't believe it's so simple. Now, there's other things that are not that easy, right? But there's just like a list of all the, it's like a checklist of all the things. That's the way the problems will be. So if you know what you're doing, like maybe you don't know how to do the integral, but at least you know isothermal means the same temperature, right? So that one's there for you. But don't freak out and get that one. Don't put a negative answer for temperature because temperatures are always in what units? At least in here, Kelvin. But sometimes they're not given to you. Like I'll do a problem. Maybe you'll do it about why it gets hot in Southern California when the Santa Ana winds blow. Okay, this is actually a problem that you can do. I talked about compressing the gas, adiabatic compression. What happens when what happens when I take a gas with an external pressure on it, and I increase the external pressure on the gas? It compresses. What happens to the temperature? It goes up. So you can do that problem thinking about moving air from the high desert down to Newport Beach, and you get the right answer. Yes? Pressure increases where temperature remains the same. Yes. Well, yes. Like if I take the ideal gas, isothermal compression. This is yes. In fact, you will be able to tell me this should this problem be on the exam. I take the volume V naught and go to V naught divided by 2, right? And the temperature stays the same. So the volume went down by a factor of 2. And what did the pressure do? By what factor? Factor of 2. Because PV equals nRT, right? And if T is fixed, if V goes down by 2, P goes up by 2. So that's how you would do the constant. I'm not writing anything. This is like a history lecture, right? So my apologies. It's going to be pretty uninteresting to watch the video. Well, most videos are not that interesting. Anyway, if I wanted to use a constant external force to compress the gas and do that problem, so what would I have to make my constant external force to get to the target half volume at the end, right? Factor of 2. So I'd start off P naught, V naught, T naught. and then I'd instantaneously jack up that external pressure to 2 P naught. And then the thing would compress, and you'd have the area of the rectangle instead of under the curve. I do all that work, that big rectangle, but then it would stop compressing right when I got to V naught over 2, right? Now, if I did it adiabatically, it's much more complicated. Okay, you'll hear more about the exam and later. But okay, so now we're in this topic 2B, and this is enthalpy. Chemists love enthalpy, and trying to understand chemists. What kind of chemist am I? I have a laboratory that has computer terminals in it, and if there's a dangerous substance in there, it's either in a bottle or in someone's old coffee cup, right? A bottle that's 750 milliliters, okay? Or you see what I'm saying? I mean, it's something you drink if it's dangerous, right? But chemists, they like different things, and they like enthalpy because this is useful when pressure is a constant. And like we talked about constant volume, heat capacity, and things like that. Like what lab do you go to where things are sealed in a box at a fixed volume? No, what are they doing? It's Friday the 13th, so we can do some, make some potions and stuff. They have their reaction, right? And there's the 1 atmosphere pressure. We should use bar, right, in this class, pressure. And so the vessel's open to the atmosphere, and there's a constant pressure conditions. And so having something that's takes pressure into account is useful. And so let's compare two processes. So let's say we have a volume that's constant. I take my gas and I put it in a container. And I make it so it's adiabatic. Actually, I don't have that thing. Let's just do that. Okay. And I put heat in. And so this is the kind of thing I would ask on an exam. I have a fixed volume gas with adiabatic walls, and I add a positive amount of heat Q is introduced to the gas. Now you might say, how did I do that if I have adiabatic walls? Well, I put a resistor in there and I heated it up or something, right? So I got the heat in there. So what is delta U? It's positive, yeah. But so give your answers in terms of like Q, T. I'll also in the exam I'll give you, if I remember to do this, I hope I do. I'll give you a list of the symbols that you can use to give your answer. Like give your answer in terms of like R, T naught, P naught, and V naught. So everything like you might have R log 2. Log 2 is a number, okay? Do you have to use your calculator to tell me what log 2 is? No, it only hides where it came from. So R log 2 is probably my most favorite answer on an exam. Okay, not some number. Okay, so what like in terms of Q, blah blah blah. What is delta U equal to? Q, right? Because that's the first law of thermodynamics. W equals 0, right? What? Yeah. So delta U is Q plus W, but what is W? Yeah. So I'll ask you that. What is W? Okay, and then if you start like looking on the front of the exam for a lot of formulas, and then scribbling on the back of the exam, no. You have to say, well, obviously W is 0, right? So now let's do it at constant pressure. So So let me draw this a little bit better. Let's keep this there. You know, there's ironically, there's an art history class in here before this class. And so that's all I'll say. It's my artistry is not always the best. So I have a P external, okay? And I put Q in, and again, you know, same deal. You know, we've got adiabatic walls, and so like here we have V naught, and here we have okay. If it's constant pressure, and I put heat in, heat goes in, temperature goes up, internal energy goes up. What happens to the internal pressure of the gas? I might ask you, what is the final pressure equals? I didn't give you enough, but if I was doing that problem, if I put a certain amount of heat into the gas, and it's at a fixed volume, you could calculate the final pressure, because you know the temperature would go up 3/2 nR delta T would be and that would be delta U, right? So this is equal to 3/2 nR delta T. If it's an ideal monoatomic gas, right? Ideal monoatomic gas. Someone's going to ask me what that is 2 months from now, so I'm going to write it. Right, so you could figure out the final temperature, you could figure out the final pressure, right? And it would be higher. But I hope you would go into the problem telling yourself, yeah, that pressure is going to be higher, just, you know, because of common sense. This pressure wants to be higher, but what happens when it actually goes up a little bit? It's no longer at equilibrium mechanically, and it expands. So the gas expands, and there's a delta V, which is the final minus the initial volume. So this one has a V final, which is greater than V naught. So what is delta U? So at the end of the day, the gas is a little, you know, it has some energy in it. And we'd have to calculate what it was. There's Q, but what did the gas do? It expanded, right? So it did work, and so we have this. And so you might think of that as like a volume tax. We all know, we're all familiar with taxes, and as Californians, we are more familiar than anybody, right? Last time you put gas in your car? Anybody get used to gas prices in a place like, I don't know, Arkansas, and then move here? That ever happened? Yeah. It's different, isn't it? But because you've expanded the gas, you've lost some of your energy, and it's like a inevitable. If at constant pressure, it's inevitable that you're going to have that situation, and so the enthalpy keeps track. And I'm going to put, if I'm just sort of BSing here, making stuff up, it's kind of like instead of gross salary, it's like your net salary. Like all your benefits have been taken out, and here's what you get. I don't know about you, but I have a lot of electronic leeches attached to my paycheck. This for the benefits, this for the more, all the stuff comes out, right? Enthalpy is like that. It keeps track of the fact that in the background, there's stuff going on. And chemists like this because they don't like math, really. So delta H is positive, delta H is negative. This is the kind of stuff they throw around. Exothermic, endothermic. We'll talk about that. Your book, by the way, tries to use the word exenthalpic. Whose idea was that, anyway? So I'll probably say exothermic for delta H negative. Heat's given off. In the background, there's being kept track of like, let's say you have a chemical reaction. You take two things in a liquid, and they react, and it produces a bunch of gas. Okay, very common thing in organic chemistry, which is why I'm not an organic chemist. All these gases, not my cup of tea. All that gas that's produced has to be brought into the world, put in the atmosphere, and you might imagine sort of conceptually a balloon being created with that gas in it. Okay? Now, not a stretchy balloon, but you have all that gas at one atmosphere. What have you had to do? You've had to make some room for it. It takes work to give off gas. And so that's why it's delta H and not delta U, because there's a tax on the delta U, which is this term, this PDV term. And so H is U plus PV. And recall that U is this thing we're calling a state function, and we'll talk about this. It's coming up, but we've already introduced this idea, meaning I have U as a function of T and V, and if I tell you what T and V are, then you know what U is. So that's not true of heat and work. That's really the path-dependent things. But if I have an ideal gas, or anything really, if I tell you the temperature and the volume and the number of moles, remember we're going to fix those for now, then you can tell me what U is. And H is also a state function. But I'm not going to say what variables it depends on yet. But I'm going to remember I have my du, right? It's just dq plus dw. And we saw last time we could write, remember this C sub v is partial u, partial t at constant v. Then we have a minus p dv, and then that p actually, just to make the mathematicians happy, is also it's the partial derivative of u with respect to v at constant t. So if u is a function of t and v, and I take its total differential du, then I get partial u, partial t at constant v dt plus partial u, partial v at constant t dv, and so it gives me that differential statement. Okay. Now if I take H equals u plus PV, and I calculate DH, I get DU. And now, I don't know what variables are really hiding underneath everything, but if I take the differential of a product of two functions, right? Like if I take like DFG, then I have FDG plus GDF. That's how I take the differential of a product of things, right? So if I take the differential of H, I have to take the differential of the PV term that I stuck on there. And so I have my C sub V dt minus P dV, and then I have plus P dV plus V dP. And I did, mathematically you define H to be U plus PV because you're trying to get rid of that minus PDV term, and then you're going to replace it with something that has a dP. So these cancel. Let me be a little fancy here. Okay. I feel like I've earned my pay for the day, and so my DH is going to be CV. I'm gonna get rid of this. My apologies. I don't want to. I'm just gonna call this. I'm gonna be vague about. That C, okay, because I don't want to call it CV. So the DV term canceled out, and it's replaced by a DP term. And so what this tells me, if I look at that, let's say we just started with that expression. And so that tells me my H is a function of T and P. So instead of being U is a function of T and V, but H is a function of T and P. How do I know that? Because when I take DH, I get a DP. So that DP here is the smoking gun that the thing has to depend on P. And partial H, partial T, and constant P is what I've called C here, and that's CP, which is the constant pressure heat capacity. That's what I don't want to call it C sub V, because that's a bad name to call something if it's constant pressure. I want to put C sub P. And also, the volume, so like we all know what volume is, right? The volume is how much space. What is the volume of your roommate, and it's probably always the best chair size, because they always sit in the best chair, right? So you have an idea of what the volume of something is, but you can, like I said, you can go home and tell your parents for Thanksgiving, guess what? Aunt Edna, her volume is actually the derivative of her enthalpy with respect to pressure if we hold her temperature constant. So that's another thing that volume is in this world, okay? In this mathematical world, and for the mathematicians, what we've really done here is something called and I'm not going to say what is this thing called. I'm not going to have on the exam define the following terms, Legendre transform, but that's what it is, and they come up in mechanics. The Legendre transform comes up all over the place, and plug your ears if you don't want to hear this. But if you're an engineer or a physicist and you know about Lagrangian dynamics, anybody hear of Lagrangian dynamics in here? Don't be shy. No one? All right. So Hamiltonian mechanics and Lagrangian dynamics are Legendre transforms of each other. All right. So that had exactly 0 people that. But you got to do your bit. Okay, so if I have a system, it has an energy, it has an H, it has a T, it has a P, it has a V, right? So a system will have all those properties, and if I start with it, if I give you a problem, so at this point now, if I give you a problem. And I tell you all those things at the beginning, and I say now I'm going to change. I change one of those things. V goes from V naught to V naught over 2. Then as long as it's a reasonable problem, you have in your capacity the ability to calculate all those different values. And it also has a C sub V and a C sub P, so we could add those to the list of things. And C sub P is the heat capacity with pressure constant. Remember, C sub V is the heat capacity. Volume is constant. So if we go back, let's go back to this problem here. V naught, T naught, and then we add heat at a constant volume. I'm I'm making up some notation here. Right. So this is V equals constant. Right? And so there's a U, there's a delta U, right, for that process. And there's a delta U, right? And that right, so the constant volume heat capacity is how much heat I put in to, like, let's say we say, okay, delta T, it's going to be 1 degree Celsius, whatever. That's the change, delta T. So how much heat do I have to put in? I have to figure out how much heat I have to put in to do that. So if I know it's C sub V times that, that's how much heat I have to put in. If I do this, so this is P is constant. Then I have a delta H. Delta T is C sub P, which is Q sub P over delta T. So just intuitively, let's put this. Which one took more heat to raise it 1 degree? Maybe I can make an exam that requires no math. Do that, yeah. Probably I won't. I'll check it out. But because of this tax, you need to add to get this one to go up 1 degree. You've got to add more heat because some of it's lost expanding the gas, right? So this is a P. So Q sub P is greater than Q sub V. And, C sub P is greater than C sub V because of that tax. And we can work out, let's work this out for ideal gas. And for some reason, and it's in, I don't know why this is. Always I use a monoatomic ideal gas for an example, and I think that's pretty much everybody. But what's an example of a monoatomic ideal gas? Argon, helium. So how much argon and helium do you encounter in your daily life? The atmosphere is what is this room is mainly what? Nitrogen. That's a diatomic, right? It was last time I checked. So why you don't use 5 halves instead of 3 halves, I'm not exactly sure. But we're going to stick with the traditions, right? And so we have U equals 3 halves nRT is one of the equations of state along with PV equals nRT for the ideal gas. And we saw before, C sub V is partial U, partial T, and constant V. And so that's 3 halves nR. And we could write this as N times C sub V bar, and that bar is molar. Probably your book uses a notation for it, but I'm too lazy to figure out what it is. But you know what I mean. So that's so the molar heat capacity of a monoatomic ideal gas at constant volume is 3 halves R, right? Now, so what is H? It's U plus PV. So that's 3 halves nRT. But what is PV? if there's one thing that, if I said PV equals, what would you have said before taking any college chemistry? Because they subject this to you. I mean, you learned this all in high school, right? Didn't they? Yeah. So PV is nRT, right? So this is actually equal to 5 halves nRT, because T is 2 halves nRT, right? Common denominator. Now, it's a coincidence, by the way, that I didn't turn it into a diatomic, did I? No, I didn't. It's a coincidence. But that is how the enthalpy depends on temperature. So if I calculate CP, constant pressure. See, now it doesn't depend on pressure, but I'm pretty sure that Craig Murray, I'm not going to watch those videos. I don't know about you, but I'm pretty sure that he talked about the van der Waals gas, right? Right, yeah. And so there, did he talk about how U depends on T and V? So, you know, for the van der Waals gas, there's some V shows up here, right? And for the van der Waals gas, there's some P's that show up in H, okay? So you have to hold those constant. But here there aren't any. So we get 5 halves nR. And so, you know, CP bar is 5 halves R. So CP bar is actually equal to CV bar plus R. So there you go. So I said that the ideal gas is constant. I said constant pressure heat capacity is bigger than constant volume heat capacity, at least for probably always, but I hesitate to say things like that because some crazy material gets invented in the lab. But for gases, you know, there's this expansion tax. So the CP is bigger. I have to put more heat in if the volume can get bigger if I want to raise it that 1 degree. And here it is for the ideal gas. All right. Now I'm going to move on. I'm skipping a lot of stuff, and if I skip it, then I would say we shouldn't really worry about it. And I kind of wish that I could. Let's see, how much time do we have left? I'm going to stop a little early because I have an important meeting. Did I tell this class where my important meeting is on Fridays? I think I did. At noon at the Anthill Pub. You know, there's the theory people have lunch together. So, do you know about the Anthill Pub? Who here has been there? Come on. Who here will be going there after hearing about this? Okay, yeah. Now, who's going to go there Fridays at noon? Because if you do go there, I'll usually be there. There'll be other people there, like sometimes the Chem 5 instructor shows up. Now, Professor Shaka is rarely there, but there's Alfredo. You know that dude? Yeah, if you've taken it before, you know, like I don't know how many times you've been trying these classes, but he comes. So if you don't want to see him, don't come. And if you don't want to see me, then don't go. But if you do go, I mean, I might, you know, don't come and ask me what's on the exam, but please feel free to come. But we're not done yet. We're not going to, early I meant like, let's give it a couple more minutes. Thermochemistry, what is that? Do you remember this? You know, where you have like delta H of some chemical reaction, right? And you do something like sum over some stoichiometry, and you have some delta H's of formation of the reactants and products. You remember this? This is what they made you do in high school, right? Do you know what I'm talking? Who knows what thermochemistry is? Raise your hands. Yeah. So, like, if I have some reaction, like, you know, AA plus BB going to CC plus DD, right? And I say, you know, delta H of the reaction. And there's always some weird symbol, right, which means it's at 1 atmosphere. It's 1 bar, okay? What is a bar? The anthill pub, okay? But in this class, it's 10 to the 5th pascals, right? 100 kilopascals. What is an atmosphere? It's like 101 something, right? It's close. So I don't know why, but anyway, this would be C delta fusion H of C plus D delta fusion, or this is formation, right? Okay, does that ring a bell? Yes? Okay. So what you do is you get a chemical reaction balanced. You go to the back of the book, you look up all these delta H's of formation, and then you combine them in stoichiometric amounts to tell you what the whole reaction is. So I will talk about it a little bit, but I don't want to, I'll give you some problem. And, I don't want to be audited. We talk about the IRS. Probably on an exam at some point there'll be a problem, okay, where you have some delta of H's of formation and you need to calculate it for the overall reaction. That's just a box we should probably check off. And there's some people that spend their lives doing it, but I think it's conceptually familiar. If I'm wrong, let me know and we'll talk about it. But I will say a little bit, but let's stop now because we all have important places to be. And come up and ask me if you have questions.